Sir, we are live now.
Still not showed up here on the feed.
Did you say that the volume should be okay? On the video should be made 0. Okay. Yeah. Is anybody waiting for us? Because if we answer the question and nobody
Yes,
is
there are
there.
5 people watching now. I'm assuming
So out of which
us.
4 are, I mean,
Four
we
are-
are 4.
We are 4.
3, 4. Because if you answer the question and that person is not there, it will not be of any use.
But the person can always rewatch the YouTube video.
Okay, okay. Oh, okay,
Because
okay.
it'll be finally be saved as a recorded stream.
Okay. So then in that case, I think we will take the
Yeah,
question.
you can take the question.
All right.
So, Ashish ji, you can take the question.
Yeah. Okay. So, the question, there are 2 questions and I will answer them. The first question is by Akanksha Dwivedi and she has asked 3 parts. There are 3 parts in the question. First is, in your experience, what are the top 3 reasons HPC code underperforms even after parallelization, like memory bandwidth, cache miss, false sharing, communication overhead, and how do you diagnose each one? So it is not easy to answer this question without somebody who has actually tried parallelizing and then found things not going well. And apart from that, since we have released only first 2 weeks videos, some of these things will be addressed later. So you can check what has been taught in those lectures, and then you may revisit this question. However, I would also like to say that when you are parallelizing the code, the first step that you have to look at is, or the first test that you have to look at is, can you break the algorithm into multiple sub programs or sub what you can say subtasks which can be run in parallel. There are some algorithms which are non-parallelizable, and if you try to attempt to parallelize them, you are not going to get any benefit. So that is the first litmus test that you have to see. Having said that, in case you are able to find the parallelism in the algorithm such that you identify multiple tasks and those tasks can be run in parallel, then it's not that if you increase the number or you make the, let's say, make the tasks, divide the task into 2 parallel tasks, it's not that the code will run in half the time, because there is always one portion which is serial initially, followed by the parallel part, and then a serial part. And in between, there could be some milestones where those tasks that finished early, they wait for synchronization. So it's typically start serial, then parallel, maybe some intermediate events where synchronization is done multiple times, and finally the last part is also serial. So if you have 2 CPUs, let's say, or 2 cores, never will the code run in half the time. It's always have certain overheads, and there is an Amdahl's law which tells how much scale up you can get. That's an ideal situation. So having said this, then once you are found that there is you are able to parallelize and you are getting some benefit in terms of saving of time, and there is some scaling also, means you keep adding more cores and the time is falling, but again it will not fall linearly. And once you have done that, then what you have asked for, memory bandwidth, cache misses, false sharing, communication overheads, these are some of the advanced techniques that possibly are not covered in this course, but we can discuss this offline, okay, based on what code are you trying to parallelize. The second question is, when porting a CPU algorithm to GPU, What are the most common design mistakes related to memory transfers, kernel launch, overhead, and data layout? How do you structure data to maximize coalescent access? So I think GPU programming is not covered in much detail in this. These are advanced techniques and beyond the scope of this course. However, if you have a specific problem to solve, we can address that when we have an offline communication. The third part is strong scaling versus weak scaling. So for a real scientific code, what scaling behavior is considered good enough, and how do you identify the point where adding node stops helping? So again, this you will get through experience. I mean, there is no clear-cut answer to it. Good enough is what? I mean, it also depends upon what if there are some codes which are embarrassingly parallel. So they will keep scaling because they are designed in such a way that you keep adding the nodes, the time taken will start falling, or you add nodes and you are able to solve a bigger problem. So there is no clear answer to this. That is strong scaling versus weak scaling. Every code is unique in its way, and of course there are means. And if you are saying that if you are designing your own algorithm, then we will have to look into those specific objectives in that specific. I mean, it will have to be looked in personally by somebody from CDAC or IIT Bombay. So this is my answer. Professor Shiva, would you like to add something to this?
Yeah, I would like to add a few points. Especially, I'll start with the third question about strong scaling and weak scaling. So if you look at the real scientific code, the scaling behavior at the end of the day boils down to the problem that you're solving. It also boils down to the numerical methods that you actually use. So sometimes it's not just good enough for us to be a good programmer. We might write the most efficient program in terms of the points mentioned ahead, in terms of minimizing memory transfer, having the most efficient code, minimizing the launch overheads, so on and so forth, having the most efficient data structures. But sometimes the actual numerical method itself underlying the problem might have bottlenecks and scaling issues just because the way the numerical method is structured. In the due course of this course, we have some specific examples and which we do discuss in the further weeks of how these problems tend to scale. There's also extensive theoretical analysis which will come up in future weeks for it. I guess points 1 and 2 have been reasonably covered well by Mr. Kuvelkar. So I don't have anything else to add over there. So I think we can take the second question, and I think that's more specific to CDAC.
Yeah, before that, Om, you have any other inputs on this?
Yes, sir. For first questions, I have some insights, sir, from my experiences. So as you had mentioned, though we do the parallelization, what are the different bottlenecks, right? So as sir has mentioned already, two perspective, like one memory related and cache related. Another important bottlenecks come into picture that is specifically with respect to communication and synchronization overhead. Because like in case of the parallel code, in that case, particular code may spend more time in barriers, reductions, and so kind of like a synchronization constraints in the codes. So for identifying those aspects, like generally one programmer can look into aspects of the MPI time with respect to the total time which has been spent by the code, or maybe like in OpenMP time stuck in the barriers or critical sections. So that kind of aspects one need to identify. And as he had mentioned, like what are the ways by which we can diagnose such kind of problems? So We practice some of the diagnosis utilities, like if you are using Intel environment, then you may go for Intel trace analyzers, or if you wish to have some open source utilities, then Tau or Scalsa can be used, right? And if you are using uh, or if you are trying for the GPU, then NVProf becomes like a handy utility to check those aspects. So this one point I wanted to add, that communication and synchronization is also critical aspect. One should look while doing the parallelization of the code and check its performance. So that's it, sir, on that part from my side.
Okay. So I'll take the question number 2, which is asked by Mohammad Khalid. He says that, sir, I have enrolled in this course. However, I currently do not have access to the required OS or computational environment needed to practice the course effectively. Whether any account remote access is possible. So the answer to this question is, please note the email address nsm-training@cdac.in. So you can write to them this email address. We can create an account for you which is valid for the duration of this course. However, the caveat is that you should be aware as to how to make use of it. We may have some videos that help in understanding how to use that system, but this course does not have support for helping students to do the practical aspects, because we do not have the manpower. Because what I hope you understand, that each student who enrolls and wants to have this access will have a unique problem that he may face, and this kind of help cannot be effectively provided over an online kind of environment. Normally, such things are done in labs. Like if IIT Bombay runs a course during their semesters, there are technical assistants who help the students. Like as we speak, IIT Kanpur is conducting a HPC course, and the faculty has got about 4 TAs who are helping the students. So one-to-one interaction is always feasible when the problem is shown to the lab faculty, and the lab faculty solves it. Trying to address this over an online link is very difficult, and that is why we have not included it as a part of this course. But given your enthusiasm to do this, we can make an account available to you on one of our clusters. However, the caveat is that it may not be possible for us to provide you online help. If you can find your way out based on some material that we provide as to how to use it, how to submit the job, you are most welcome. That is the answer. Uh, uh, Professor Shiva and Om, would you like to add anything
I
to?
think that's perfectly well
Yes.
answered.
Yes,
Yeah.
that's perfectly fine, sir.
Okay. So now we will check whether there are any questions that are asked in the chat window. Not yet.
So we will wait online for
Yeah.
people to ask questions.
Sure, sure. We'll keep monitoring the chat window.
I think they're going to conclude the session. Can you hear me?
In half an hour? Okay.
No, I think nobody's really watching. They just messaged me. And our
Okay.
chat also, they're asking, should we stop? I think we can because nobody's there.
Okay, I think we can conclude it then.
Yeah, we can conclude. Thank you.
Or they can, I mean, those who want, they can always watch it later for the questions,
That is
answer the
already
question there.
Yeah, that is there. And plus, I think this is the first initial week, right? There might not be
So,
too many questions.
Too many questions. Correct.
The next,
All right.
next interaction might be.
Yeah. Okay, go ahead.
Okay, thank you. So we'll leave the call. Is
Yeah,
that
okay. Yeah. Bye.
Bye.
Nice.
Okay, sir. Thank you.
Thank you.
Thank you.